So section 4.5 in some sense isn't anything new, but that's really stretching the truth a bit. What we're going to do is take essentially everything we've learned in chapter 4 so far about rules of exponents. When to add exponents, when to multiply exponents, when to subtract exponents, how to make negative exponents positive, how to reduce a radical that has a variable by dividing the index by the exponent. We're going to take all of those rules and use them to solve problems. And the big issue with the problems in this section is we're going to have lots of fractions to deal with. So it's going to be, I think, a challenging section. So I'll do my best to make it not challenging. We'll take it in little bite-sized pieces. And we'll just jump into it. The first few problems are going to use the most recent rule. At the end of section 4.4, we learned how to make radicals we learned to simplify radicals. We could do, something like the 4th root of x to the 12th. And we simplified by using the rule that says if we have a radical, we can turn that radical and we can get rid of the radical by dividing the exponent divided by the index. So the 4th root of x to the 12 is x to the 12 over 4, which is x to the 3rd power. I was very careful in section 4.4 to make all of the divisions not come out to fractions. That doesn't have to happen. If I'm asked to simplify a radical, it's possible that doing the division of the exponent divided by the index produces a fraction. For me, that's generally not preferred, but it's a skill we need to be able to have. In the first few problems that we get in section 4.5, the instructions say write the expression. An expression is a problem without an equal sign. Write the expression using a rational/fraction exponent rather than radicals. And it's not particularly hard to do, but it produces fraction exponents more often than not. So if I had the expression the 5th root of y squared, if I wanted to simplify it just like I simplified the 4th root of x to the 12th, well, I would form a fraction. I'd stop writing the radical and I'd create a fraction exponent by taking the index and dividing it into the exponent. So the 5th root of y squared is just y to the 2/5. So I'm creating a fraction exponent. The index becomes the denominator of the fraction. And if the fraction doesn't reduce, it doesn't reduce. In the next version of this, write 5 times the 4th root of y as a radical. I have to really, in my mind, separate the coefficient of 5 from the radical because it's not going to be part of the fraction exponent. The radical part, I might have to slide in the exponent of 1 that's implied to help myself get the radical form. And then I'm going to turn the radical into a fraction exponent by dividing the exponent divided by the index. And then I could suppress the times sign. So 5 times the 4th root of y is the same as 5y to the 1/4 power. If I was doing this third example, there's a couple ways to do it, but probably the way that's easiest to follow is use the strategy that we had in section 4.4 that allowed us, if there was multiplication inside a radical, to break the radical up into multiple radicals. And this rule does need each radical to be a real number, and we'll just assume that's the case. And then I'll set each radical up so that I can get the fraction exponent. And for me to get a fraction exponent, I need to see the exponent of the term under the radical. So if it doesn't have one, I'll sneak a 1. And now I can write this as 7 to the 1/4 times x to the 3/4, which is 7 7 to the 1/4, x to the 3/4. The times sign doesn't need to be there. It turned out that's not the only way to solve that problem. There's a way to solve the problem that would give this as an answer. I kind of hesitant to show it, but let me show you it anyways. The other alternate way to get this simplified to this answer, I could have thought of this problem instead of as two separate radicals. I could think of this problem as having a parentheses with an exponent of 1. This is equal to the problem because anything to the first power is itself. And if I have the entire radicand in a parentheses, then I can simplify by dividing the exponent by the index, and I'd write that answer. They're both equal to each other because here, to clear the parentheses, I would attach the exponent to the 7, and I would multiply the exponent for the x, and it turns out that 3 times 1/4 is 3/4. Maybe that's a little complicated, but it's worth seeing, just in case you remember this stuff and this is what you do. So each of the problems between 1 through 8, they just want me to do this, make a radical out of something, make a fraction exponent out of a radical. So for number 2, I'm just going to say this is y to the 3/4 power. For number 4, I'm going to emphasize this is 2 times the cube root of y to the 1st. I need to keep the 2 in my mind separate from the fraction exponent. I don't really need the times sign, but I'm just trying to put some distance between the fraction exponent and the coefficient because the coefficient doesn't get a fraction exponent. In number 6, the 2 being under the radical makes it get a fraction exponent. It's now part of the radical, and when you're part of the radical, fraction exponents happen. If you're not under the radical, you're not going to get a fraction exponent. In 6, I'm going to think of this as the cube root of 2 times the cube root of x squared and sneak the implied exponent of 1 on the 2. Now this is going to be the cube root, whoops, now I can make fraction exponents. The cube root of 2 to the 1st, I can write as 2 to the 1/3. I was going to write a times sign, but it's going to be implied, so I'm not going to write the times sign. And the cube root of x squared, I can say is x to the 2/3. For problem 8, I think of this as 5 times the 6th root of 7 times the 6th root of x to the 5th. I remember that that 7 has an implied exponent of 1. And now I can make fraction exponents. This is going to be 5 times 7 to the 1/6 power times x to the 5/6 power. This times I don't need, but this I need something to represent times, otherwise it's going to look like the number 57. So either a parentheses to represent this times might be nice, or a times sign to represent this times might be nice. But between the 7 to the 1/6 and the x to the 5/6, I don't really need a multiplication. But if I'm not using parentheses to signify multiplication of the 5 and 7, I need something to do that. The next few problems we're going to go in reverse. We're going to be given a problem with a fraction exponent, and we're going to use the rule in reverse. Basically saying, if I have a fraction exponent, I can turn that problem into a radical. And how would I turn it into a radical? We'll do the reverse. Instead of taking the index and making it the denominator of the fraction, I'll take the denominator of the fraction, exponent, and make it the index. And everything else is going to become the radicand. Because 2 squared, the 7th root of 2 squared would simplify to 2 to the 2/7 power. So to write an expression with a fraction exponent using a radical, it's just the reverse. And then of course if I get an exponent I know how to reduce, I might as well reduce it. When I have coefficients and non-parentheses, I need to really, in my mind, separate the coefficient from the term with the fraction exponent. If I wanted to make 4y to the 1/5 into a problem that has a radical, I keep the 4 separate from the radical because it doesn't have a fraction exponent that applies to it. And then under my radical, that's going to be a 5th root, I'll get a y to the 1st, and the exponent of 1 isn't necessary. For this third example, I could rewrite it, but I don't have to rewrite it. Because of the parentheses, the 4, it's inside a parenthesis, so the fraction exponent applies to both it and the x. When I go to rewrite this third example, the 4 is going to go under the radical because it's inside a parenthesis, whereas the problem above it, the 4 doesn't belong under the radical. And in this third problem, anything to the first power is itself. So let's do a few of these. Take these radicals, take these fraction exponents and write them as radicals. And number 10, the denominator of the exponent is 4, so that's going to become the index. Everything else is going to become the radicand, because if I gave you this, you can turn it into that. And of course I can reduce this, because 2 cubed is 8. For 12, I can make this the 5th root of y cubed. And I can't really simplify more than that. For 14, I have to really emphasize that the exponent of 1/3 doesn't apply to the 1. So I'm separating them just so you can emphasize that. And when I go to write the radical, the denominator becomes the index, so the index is going to be 3, and the rest of the variable sneaks under the radical. I don't really need that times, but I like it there just to show the separation that I want to see. So 14 rewritten as a radical would be 3 times the cube root of y. 16, because the 3 is inside the parentheses, when I go to make the radical, it's going to wind up under the radical, as opposed to in 14 where it wound up in front of the radical. So this is going to be the cube root of the quantity 3y to the 1st, and anything to the first power is itself. So I'm just going to rewrite this as the cube root of 3y. Now we're going to get into some numerical stuff that has fraction exponents, and take the time to turn the fraction exponent into a radical and then simplify using whatever strategy for simplifying. So I wrote first 49 to the 1/2 power. Usually I say 1/2 power equals square root. Anytime I see a 1/2 power, I think a square root. Why is that? Because if I have a fraction exponent, I can turn it into a radical. The radical form of 49 to the 1/2 is the second root of 49 to the 1st. The index of 2, if it's not written, it's assumed. The exponent of 1, if it's not written, it's assumed. So 49 to the 1/2 ultimately is the same as the square root of 49, and that's 7. The next problem wants me to simplify 64 to the 2/3 power, so I'm going to make the radical form of it. The index is going to be 3, that's the denominator of the fraction, and the radicand is 64 squared. 64 squared is a monster number. There's 2 ways to reduce this problem. When I have the cube root of 64 squared, there's 2 things I can do. I can do 64 squared, which is 4,096, And then I can do the cube root of 4096, which is 16. The alternate choice I could have had is I could have done the cube root of 64 first, which I could even get off my sheet. The cube root of 64 is 4, and then do the squared. Still get 16. So when I'm writing fraction exponents as radicals, if there's an exponent under the radical, I have my choice of doing the radical first and then the exponent second, or the exponent first and the radical second. They're equal to each other, radicals and exponents. When we started doing the PEMDAS, I said we're going to treat the radical like an exponent. So they're kind of flip-floppable. You can do a radical before an exponent or an exponent before a radical. Some nastiness here. This problem, 243 to the negative 2/5 power, I have to use the rule that says x to the negative n power is 1 over x to the n. I'm not going to work with negative exponents. I'm going to make negative exponents into positive exponents. So 243 to the negative 2/5 power is 1 over 243 to the positive 2/5 power. Then I'm going to make the radical. It's going to be a 5th root because the denominator of the exponent is 5. The radicand is going to be 243. And then I'm going to do the 5th root of 243 first. And the 5th root of 243 is 3. So when I'm dealing with here, 1 over the 5th root of 243 squared. First I'm going to do the 5th root, then I'm going to do the square. The 5th root of 243 is 3, and then I'm going to do the squaring. 3 squared is 3 times 3, which is 9. The fourth problem on this list, there's a physical times between the 2 and the fraction, or the fraction exponent. I'm going to turn the fraction exponent, the negative exponent, into a positive exponent by forming a fraction with a 1 in the numerator. Then I'm going to make the fraction exponent into a radical. 1/2 powers turn into square roots. Then I'm going to do the square root. So this piece right here, the 2 times 25 to the negative 1/2 power, 25 to the negative 1/2 power simplifies to 1/5. The negative exponent turns the 25 to the negative 1/5 into a fraction. The negative 25 to the negative 1/2 turns into a fraction, and the 1/2 power turns into a square root. And then 2 times 1/5 is the same as 2 over 1 times 1/5, and that's 2/5. Let me just jump into the problems. I feel like I'm rushing these, and let me just jump into these and go slower. So for 16, I'm going to write this as a radical. For 18, I'm going to write this as a radical. The radical form is the square root of 16 to the first. Apparently, I really need to slow my mind down. That's going to be the square root of just plain 16. And the square root of 16 is 4. I'm going to use my radical sheet, but I'm trying not to use my calculator. 20 wants me to find 64 to the 4/3 power. So I'm going to do the cube root of 64 to the 4th. And I'm going to emphasize that I'm going to do the cube root first and the 4th power second. Because if I try to do 64 to the 4th power, I won't even want to write that down. I'd probably write it down wrong. So algebraically, if you have an exponent under the radical, you can do the radical first and apply the exponent second. So I'm going to apply the radical first. The cube root of 64 is 4. And then I'm going to do the 4th power. And 4 to the 4th power is 256. That's on this sheet as well. So without pressing a single button, just using the knowledge I have on the sheet, I can get the answers that I need to get. 22 wants me to simplify, and I see a negative exponent. I know that negative exponents I'm going to turn into fractions. Negative exponents almost always turn into fractions. They almost never turn into negative numbers. And then I'm going to turn the fraction exponent into a radical. The radical form of the 8 to the 1/3 power is the cube root of 8 to the first. I don't need to write the exponent of 1. That's going to be assumed. So this is really 1 over the cube root of 8. And cube root of 8 is 2. So problem 22 is going to reduce to 1/2. 24, I get a fraction exponent and a negative fraction exponent. The negative exponent I'm going to turn into a positive exponent by creating a fraction. So 49 to the negative 3/2 power is 1 over 49 to the 3/2. Now I'm going to make the radical from the fraction exponent. It's a square root, so the index of 2 can be assumed. And I would have my choice of doing the square root of 49 first or doing 49 cubed first. 49 cubed is bigger than I care to write. It's not something I would ever have written down. So I'm going to do the square root of 49 first, which is 7. I'm going to turn the square root of 49 in the denominator to a 7. And then I'm going to cube, and 7 cubed is 343. So all just having knowledge that's at my fingertips that I'll give you on the test can reduce these radicals, and it helps me understand the manipulation better if I'm not pressing buttons. For 26, I need to make the negative exponent positive by creating a fraction with a 1 in the numerator. I keep the coefficient of 3 separate. The 8 to the 1/3 power, I could make it have a radical. It'd be the cube root of 8 to the first, which is really just the cube root of 8. The cube root of 8 is 2. So now I can think of this as 3 times 1 over 2, because the cube root of 8 is 2, which makes this 3 over 1 times 1 over 2. If I'm going to multiply without my calculator, I make both pieces a fraction. I multiply across the numerator. 3 times 1 is 3. I multiply across the denominator. 1 times 2 is 2. Getting ready for part 2, I'm pretty sure we have a few more problems, maybe 4 or 5 problems to deal with. For 28, I'm going to write this as 15 times 1 over 81 to the 1/4 power. I'm going to make the negative exponent positive by creating a fraction with a 1 in the numerator. Now I'm going to make a radical from the fraction exponent. The radical is going to be the 4th root of 81 to the first, which is really just the 4th root of 81. The 4th root of 81 is 3. So this is going to give me 15 times 1 over 3. The radical reduces to 3. This is 15 over 1 times 1 over 3. And I could actually cancel. This 15 and that 3 will cancel. The 3 I'll divide by 3 and get 1. The 15 divided by 3 and I'll get 5. I don't need to write a fraction anymore because I only have 1s in the denominator. I just need to multiply the 5 and the 1 that I have circled. So my answer is going to be 5. Here's where I stopped explaining because I felt like I was getting a little bit crazy. So let me turn 30 into a radical. It's going to be the cube root of 8 over 27 squared. I'm going to do the cube root first and the square second. So I'm going to do the cube root of 8 over 27, and then I'm going to square it. Now I'm going to get rid of the cube root. I'm going to do the cube root of 8, which is 2, and the cube root of 27, which is 3. So I'm doing the radical first, cube root of 8, cube root of 27, and now I'm going to square using a rule that we learned a few sections ago. This is going to be 2 squared over 3 squared. So this is going to be 4/9. They feel easy to me, but boy, I've done a lot of these. I know when I learned these, they couldn't have been easy. Let's do 31 together. For 31, I'm going to write this as the square root of 25 over 49 cubed. I'm going to do the square root first and then cube second. I don't need to write the index of 2. I know both the square roots. The square root of 25 is 5. The square root of 49 is 7. And now I'm going to cube. I'm going to make this 5 cubed over 7 cubed. Don't need my calculator. 5 cubed is 125. 7 cubed is 343. So this is 125 over 343. 33 and 34 are going to use the rule that if we have a fraction with a negative exponent, we can make the negative exponent positive by taking the reciprocal of the fraction. Not taking the reciprocal of the exponent, but physically taking the reciprocal of the fraction. So 8 over 27 to the negative 2/3 is 27 over 8 to the positive 2/3. Reciprocal of the fraction, make negative exponents positive. Now this is going to be the cube root of 27 over 8. And I'm just going to put the squared outside the exponent so I can do the cube root first. The cube root of 27 is 3. The cube root of 8 is 2. And now I'm going to do the squaring. I'm going to square the 3 and square the 2. So these are very repetitive and systematic. Hopefully I gave you enough problems so that you're starting to feel like you can do these without me doing them, because that's what's going to need to happen. Let's do 35 together. 35, I see a fraction with a negative exponent. I'm going to make the negative exponent positive by taking the reciprocal of that fraction that's given to me. Now I'm going to make a radical from the fraction exponent. And it's a square root problem. I'm going to do the square root of each number first, and then I'm going to cube. I'm going to do the square root of 49, which is 7. The square root of 25, which is 5. And then I'm going to cube the 7 and cube the 5. Have my sheet off screen. 7 cubed is 343. 5 cubed is 125. Let's pause and do a part 2 because we're pushing 30 minutes. I hope the part 2 is short. I think it's going to be short. There's only kind of one new concept.